All right. Okay. Today we will go for the this topic, which is product architecture. Product architecture is the one topic for the product design and development. So I believe you already studies about the conception for product concept, how to design the concept, and then specification. And then before you further for master class in the bachelor, also you have a class for the product manufacturing engineering. So you learn about product design as well, and then how to design the step of product design in this in that particular subject. So I think you can recall back the note everything for the product design, because that product design you learn in the manufacturing engineering is very related to the product design development as well, in terms of conception and specification. So today we will go for the product architecture. And in this topic, you will learn how to do the some what we call it, the schematic design, how you will create the product concept using this product architecture. So we use the same teaching material. We use a product design and development books from Carl Theories. I think you get that books from Moodle. Also, we upload this book for your reference. So in this book, in the chapter 10, you can see this product architecture. Okay, and then I will cover for the rest product. In the after product architecture, we go for the industrial design, and then we go for the design for manufacturing, DFM, and then last we have a product development economics. So this is my topic actually, and then we have one industry talk for you all that is related to the product development economics topics. So we have the guest from Petronas, what we call it, from the section improvement from the Petronas, Malaysia. So they will talk about Lean Six Sigma. They will share about the experience Petronas handling the production using the Lean Six Sigma. So in terms of product development economics, so what is the related to when we're using the Six Sigma? So there will be interesting talk, I think, from our guests. So you can have one industry lecture at the end of this season. All right. Okay, for the product development process, it has, I think you already know, we have this typical process for the development. We have planning, concept development, system level design, detail design, testing, and refinement, and product ramp-up. So for the product architecture, so we have to conduct in the earlier stage in terms of planning, concept development, and system level design. That is the earlier stage before we go for the design. We have detailed design here. After we have a detailed design, we have select the raw material. We go for the prototyping, evaluation, testing, and then we have a production to mass pro our product. That is a product development process. And then for the in terms of planning, we have a platform decision, for example, and then concept decision. You already learned this one. And then system level design, we have a decompression decision. So actually the product architecture will begin in terms of planning, concept development, and system level design. So you can have an example from the textbook as well. You can find out in the Purist textbook about they describe how Hewlett Packard they designed the printer, desktop printer. So a production team with Hewlett Packard, they have a printing division. They was considering how to respond to the pressure, the simultaneous pressure to increase their product variety, because the printer you see in the market, they have several models, several types. So they have pressure to increase the product variety and to reduce the manufacturing cost. How to reduce the manufacturing cost with the product variety. So they have the development team have their task to respond to the pressure, how to increase the product variety and to reduce the manufacturing cost. So inkjet printing have become the most dominant technology at the time. They have a small office printing involving with the color. You can see they come out with the from black and white printer. They gave color, printing color, and then they have excellent quality. You can print ever a photo with quality. So there is the improvement Hewlett Packard did. Not only Hewlett Packard, but Canon, other makers brand printers as well. So they give now you can obtain the printer at the lower cost. You can buy less than 200 ringgit, $200. So now everyone can buy printers, can use printer in house, can print the photo. Use your handphone, you can print out the photo. You can easily doing your job. That is the what you call it, innovation or improvement that taken by the printing company, especially for the Hewlett Packard. So we use this product architecture example in our class today to describe how they develop the product, how they plan. So in this class also we will have to focus how to establish the product architecture. So we have a definition, we have a modularity, step for creating, how to create the architecture, and then related system level design issues. So the purpose of the product architecture is to define the basic physical building blocks of the product in terms of what they do and what they interface to the rest of the device. So we will see the concept, the definition, the interfacing. So we will cover all this in this outline. And then product architecture is the assignment of the functional element of the product, of a product to the physical building block, And then the physical element of the product are typically organized into several major physical building blocks, which we call chunk. Like you play puzzle. They have block, and they have can combine. You have one puzzle, you can combine, and then we can step for each one, and then we can combine. So there is a call it chunk, physical block, a product are typically organized in several major physical building block, which called chunk. All right. So each chunk then made up, they will make up and then make a collection components. They will give a product, one block of the product. So the component that implement of the function of the product, they call is the product architecture. The architecture of the product is the scheme by which the function element of the product are arranged into the physical chunk and their interaction among them. They have an interaction among themselves for every chunk. So that is the definition of the product architecture. And then the arrangement of the functional element into the physical chunk will become the building block for the product or family product. So they will have a module of the chunk. The step over, they will come to, and then we combine together, and then we become one product. So for example, of the printer right now, some of the function elements from the printer, like store the papers, for example, they have to store the papers, and then from the paper, they have a roller to feed the paper inside the printing areas, and they have the ink place, this X and Y to print out the materials to the papers, to print the inks to the paper. And then communication, they have communication host to the computer. So all these functional elements are usually described in schematic form. So we will learn later on the schematic form, how they interact each other. So we will describe using the schematic form, and then before they are reduced to the specific technologies, component, or physical working principle. So all these module will become building block and then give one product. That is a product architecture. So let's think about the printer just now. The question is how to increase the variety, reduce the cost, so of the color printer to compete each other, because I think you learned already how the product cycle is. When they have a growth, they have a maturity, they have a decline stage. At a decline stage, they need to make another version, another model to sustain. So to reflect to that, to increase the sale per year, so the makers, the product makers should think about how to sustain in the market. And then, however, the market matured and then commercial success required that printer to be turned to more focus on the market segment. They will need to focus on the market segment, and the manufacturing costs should reduce. They should have a variety, more variety. They should reduce the cost of the production, because you need to sell a more cheaper printer to sustain in the market. And then in consideration in their next step, the question raised is how would the architecture, the product, impact the ability of the offer or the product variety? How to make a various product, and then how would the architecture of the product impact their ability to complete the design within short time, for example, within 12 months. And then how would the architecture of the product influence their ability to manage the development of process, for example. So that is what we need to answer during this class when we considering the product architecturing. So I hope you can relate all these questions during my class, and then you can find out how to offer the various product variety, production cost, lead time, and then development process management. Okay, I think you're familiar with this one. You see in the textbook as well. You can find out in your life if you have bicycle. You can see this product. Okay, perhaps the most important characteristic of the product architecture is their modularity. Modularity. That is very important characteristic. Modularity. So consider the two different design for bicycle, because I said just now this product for the brake and then for the gear shift for the bicycle. So this left one is a modular, right one is the integral. So you can see the difference. I will explain. So by this, considering these two different design for bicycle brake and shifting gear control here, so you can see that in the traditional way, the previous design, we have a separate. We have separate between shift control and then brake. They have separate design, separate chunk, separate element. So separate block. They have a separate block, chunk, or element. So when we design one part by part. We design only for brake, for shifting. So we need to see individually. So we call it modular, modular part by part. So the brake function are allocated separately. So in fact, they are mounted in the separate location in the bicycle as well. So in the handle, you at the bicycle. In the left, they have gear shifting, and then you can use your finger to grab the brake as well. So that is the typical design for brake and gear shift. The location also they design as well to easy to use when you ride a bicycle. So the design we call it a modular design, and then this is a integral design. So after several improvement, innovation, you can see this design. Maybe your bicycle use this kind of design for gear shifting and brake. So they have in the similar chunk or similar part, they combine all these functions together. They have a brake function, they have gear shifting function inside this design, this chunk, this element. So we call it this one as a integral design. So what difference from modular and integral? So you can see here the function, they have two functions. At the separate block, they combine to one block to be all the function all together here. So, and then you can see also the design very stylish, ergonomics, and then you can see the part also reduced from 1 to 3, they have only one. So there is different, you can see on the physical. And then the allocation of the part also, they can put at the similar, the handle, and then you can easily use the gear shifting and then brake together at the same time. So in this case, they consider the motivation of aerodynamic design, ergonomic concern of design. So the function from the medulla, they have keep the same function, but the element they will reduce from 3 element, 3 chunk, they use only 1. From 1 chunk, they come out with the 2 or 3 function, but now they have two functions here. They keep two functions, but they can have more than that. So that is the modular and integral design. So from this, you can have these summaries for the modular and integrated design. So a modular architecture has a following properties that the chunk implement one or few function element in their entity. So the interaction between chunk are well defined. So the interaction for a shift, only for the gear shifting, they only do that function. For brake, the function only for braking. So well defined function for each chunk, but the interaction between chunk are well defined, so they can be used, can be interact, and then the function are specific. And then generally the fundamental of a primary function of the product, they can describe in the modular for the like I said just now, for the brake, for the shift, gear shift. So that is specific for that one. Okay. The most modular architecture is the one in which each function element of the product is implemented by the one physical chunk, and then which there are a few well defined interaction between the chunk. And then such a modular architecture allow a design change. You can make changes on the design anytime, easily, to be made to one chunk, so without requiring to change to another chunk. So for example, you want to make improvement on the brake only, you can take the brake block, you can do a design process, and then you can make improvement, you can fabricate it, and then you can put in the handle, and then it can connect together with the chunk of the shift gear. So without interaction of the shift gear, you can do a modification of the brake chunk. So the product will can be function. Normally, when you take out the brake, the gear shifting chunk can be functioned either without that particular chunk. But for the modular, for the integral design, so you cannot do that. The chunk are designed quite not independent. So they have interrelated with other. So for modular, they have independent design, but for integral, they have a integrated design. So the integral architecture, they have a functional element of the product implemented using the more than one chunk. They have a single chunk implement many function elements. Like now, they can be a brake, can be a gear shifting inside one chunk. So the interaction between chunk are ill-defined and maybe incidental to the primary function of the product. So when you do, you cannot do simply improvement for one function only. So you need to take all those chunk, because they have related with the gear, with the brake. So you need to take out, and then you need to do improvement on that, and then you consider the improvement for whole part, and then the part cannot operate without that chunk. So they're not independent, they just integrate each other. So that is the difference between modular design and integrated design. So from there, we have factor affecting architecture modular. They have in terms of product change. So just now they have product change, product variety, component standardization, product performance, manufacturability, and product development management. That is a factor effect your architecture modularity. So the decision about how to divide the product into the chunk and then how much modularity to impose to the architecture are important to the entire enterprise, such as a product change just now, product variety, component selection, product performance, manufacturability, and product development management. The architecture of the product are used for making decision about marketing strategies, manufacturing capabilities, and then product development management. So for the product change, the chunk are typically building blocks for the one product, but the architecture of the product define how this block relate to the other function of the product. The architecture also define how the product can be changed, So modular chunk allow changes. The modular can be changes made to a few isolated function element of the product without affecting the design of other chunks. So you can do a design change when you want. So without any interrupt to another chunk. So you can do product changes. So the changing for the integral chunk, they will influence many function elements inside, like gear, shift, brake just now. They come together. So when you do a product changes, they will affect to many function element, and it require changes to several related chunks as well. So some of this one you need to consider the reasons, why you want to update, why you want to change your product. So maybe for the upgradings, for the add-on the function, new function, for adaptation, new environment operation, wear and tear, consumption, flexibility in use, and reuse, recycle, creating a secure product. So that is, you need carefully consider the reason before you do the product change. But there will be effect to the product architecture of modularity when you do a product changes. Okay. All right. And then we go for the product varieties. So varieties refer to the range. You already learned in the manufacturing engineering, the manufacturing, how they manufacture the product using the job shop, using the mass production, batch production, mass production. So they are come out this type of production because of the varieties, because of the product varieties, because they need to cater all the model, the demand from the customer based on the user demand. They come out with the variation of the product, because maybe myself, I need different type of printer. Yourself maybe thinking about different type of printers. So they design based on the requirement. The variety refer to the range of product model and the firm, the company can produce within the particular time of period. So in response to the market demand, in response to the customer requirement, in response to the users. So normally they introduce, you learn in the product cycle, during the introduction stage, they just introduce the one model, one model only. So the user keep using, and then they give a feedback, and then they will go for the growth level of the product cycle. At the growth step, they come out with the varieties, add-on, the function, more model. So more variety can be selected at that time. So they will have more buyers to buy when they know about that product. So that is the demand come, and then they go for the maturity. All users use their product. So the product built around modular product architecture can be more easily make a variation. The modular is very good, what I call it, aspect. They can be used for the variation more product, because the chunk design very specific for their for specific elements, specific function. They can do for the variation of the product without adding tremendous complexity to the manufacturing system. For example, you can see this wash. This is wash maker, wash wash. You can see they have a different model, maybe for male and female for I think, but you can see what different from there. Swatch produce hundreds of different wash model. So, but they can achieve the variety at the relative low cost by assembling the variant from the different combination of the standard chunk. For example, the face, the gears, the screw, the band. So they have a different type, different type of wash, but using the standard one. Casing, for example, you can see here they have a standard casing, but inside they have a different design of the face there. But they use the same gear, for example, inside. So that is I will explain about the standardization later on, how they use conduct the standardization. And then the large number of different part, like I said just now, the band, the hand, the screws, can be combined with another case. For example, another casing here, you can make another brand, another variety for the wash. So they end up with the combination strategy to create many product variety. So the user can select based on their taste. They also can produce a different band for different type of user. For example, you can see nowadays so many wash. You can see the variation of the model of the product. Okay. And then another is a component standardization that I said just now. From the wash, we have a component standardization. So that is also factor for affecting the modularity, architecture modularity. So component of standardization. Component standardization is the use of same component, use of same component or chunk in the multiple product. So like just now I said gear, and they have screw. That is a standard part for the wash. And they use that one and for the another wash as well. So they use a great combination of the standard part. So if chunk implement only one of the few widely useful function element, then the chunk can be standardized and used in several different products. They can use for another product as well. So standardization allow the manufacturer to manufacture the chunk at high volume. So there is a economic production. They produce at high volume. They can reduce the cost of production. So that's why product component standardization is very important. Very important in manufacturing to give more benefit in terms of price, profit to the manufacturer, and can give a less price to the users. That is the benefit you can get when you consider for this standardization, and can produce the more product with a high volume. And this of course, the user, the seller can sell at lower cost to the user. We can increase the productivity and increase the quality of the product as well. For example, wash just now, the movement Identically for the Swatch model, they have several component part at a standard part, and the component standardization may occur outside companies. They have a Swatch company, they have outside company called vendor. They do a product supply to the Swatch. They make a standard part. So they not only sell to the Swatch brand or Swatch manufacturer only, they can sell to the Casio, sell to the another brand of the product, Tech Higher, for example. So they can make a product component of standard component by component standardization, and then can produce a high volume, and then can sell in the lower cost to their vendor, their manufacturer. So the vendor also can get with the cheaper price, so the watch become cheaper. So that's why they're not involved inside, but the component of standardization also can involve outside from the company. We call circle or supply chain to that Swatch or watch supply chain. For example, we can see others than gears, others than screws. We can see also battery suppliers. So for watch, they use a common battery, for example. So not the watch company like Swatch or Casio made the battery. Perhaps they have another vendor made the battery. They make a company for making the battery and then supply to the several watch company to use the same battery. So they call it the made by supplier in the standard battery that can be used for all watch company with the low cost battery as well. So that is example component of standardization. All right. And then product performance. Product performance. So what is product performance actually? So we define the product performance as how well the product implement or intend to function. When you create something, you see the function of the product. How well it functions, that is a performance. So typically, product performance characteristic is like you can see, we can measure by speed, efficiency, life, accuracies, noise. So that is all the performance characteristics. So we can see that how well our product, and then the integral architecture facilities the optimization of the holistic performance characteristic, and those they are driven by the size, shape, and then mass of the product, such as the characteristic include acceleration, for example, energy consumption, aerodynamic, drag, noise, and aesthetics for the product. So that is how we use or see the product performance normally for the integrated design. As example, you can see here the motorcycle here. You can see there is a tires. Clearly, you have handle frame. They have frame to combine the frame chunk with the tire chunk, and then we have another chunk for the engine. They are very have a separate function with the separate chunk, and they give us separate elements. So considering this one, a conventional motorcycle architecture design, they have assigned a structural support. Like I said just now, they have frames for support, and then they have engine for power conversion, to convert the power, transmit the power to the tire. They have gear here. They have a power conversion chunk to give to transmit the power and then to make the bike or motorcycle move speed. So that is what I call it, the basic, the fundamental of a motorcycle. So there is a BMW R 12,000 1100 RS, I think. Okay. So from here, you can see the improvement from the several years. You can get this type of a motorcycle. So there is the new, the latest, the what I call it, ergonomics, stylish. So the architecture for the motorbike already changed. So you can see here the several functions already combined together and then can get part reduction. For example, you can see here motorcycle assign both the structure and support function and power conversion function to transmit the chunk as a transmission chunk. So the engine become their frame already in their design. So from the previous design, they have a separate chunk for the engine, separate chunk for the frame. So they just combine, become one to be a frame support, and then to have a function as a power transfer conversion element to transmit the power to the from the engine to the tires as well. So they combine the element. Of course, the design have several process, but the idea is there, and the combination of chunk from the two become one, and then but the function maybe not only one, but they have two or three function together after they combine that chunk, and then they can reduce also the design can exploit the properties, the casing to eliminate the extra size. They can eliminate the extra size of the motorcycle and the mass of the when they're using a separate chunk right now. Because if they uses the separate chunks for frame, maybe they have extra mass. So engine mass and the frame mass. So they combine together and they can have more light bike, light motorcycle, and then can increase the speed. Then can have a fuel consumption in terms of their design. So that is all related to the design and how they combine. They make a integral design to this motorcycle to exploit everything. And then the practice of the implementing a multiple function using the single physical element is called function sharing. They share all those functions in the one chunk or two chunk. So they call it function sharing. And then the function sharing is very good practice when you make innovation or modification using the integral modularities, modulus, integral design, sorry. And integral architecture allow for the redundancy to be eliminated through function sharing. So you can see the redundant redundant function or redundant chunk you can eliminate. You can combine using that function sharing just now. For this case, they have frame and then they have engine separately. When you eliminate one, you just have engine and a frame together. So allow you to do a geometric nesting for the component and then to minimize the volume of the product occupancy. So of course they become reducing the mass, increase the powers. So that is the function sharing. Then they can reduce also material usage as well. Instead of frame just now, they use a lot of material. When they combine, use the engine as a frame, they use a casting aluminium, for example, react as their frame when they design together. Of course, the function of engine still there, but they still bring the frame as a connecting between two tires together, and then to minimize the potential using of the material. So they will reduce the cost of manufacturing as well. They will reduce the cost. All right. And then the production also can make a very high quality, and then can produce with a high volume production, and then can sell more with lower price for this kind of motorcycle. So maybe this one at the prototype, they need to sell at the very expensive. Well, but nowadays they can sell at lower price. Even the design is very good, stylish before previous one. Okay. And then the most important part is manufacturability. So when you design something, you need to end up with you need to think how to manufacture it. What machine you want to use, what tool you want to use. That is very important when you design something. When you design something, you need to think the element of how to manufacture, how your plant ability. If you are engineer at the company, you need to see the machine inside your company. You need to see your tools. You need to see your ability to produce the product when you do a design. So that's why you learn about concurrent engineering. So when you design something, you need to involve another section. That is concurrent engineering. You need to involve from production engineering, from marketing, from your customers. So when everything involved inside your design team, you can get more input, and then you can design nice product, and then that product, of course, can be manufactured. So the important is manufacturability. So this topic also we have in the separate section for design, DFM, design for manufacturing. So we will have that topic. So I will explain more on that topic later on. But in additional to the cost simplification of the product variety just now, and component standardization as described before. So the product architecture also directly affect the ability of the team to design each chunk that can be produced at lower cost. That is very important, lower cost. So the task of design engineer is very important rules. Need to come out with the lower cost product for the separate chunk design. And then one more important part I said just now is the FM strategy involved, and to minimize the numbers of parts. When you do a product function sharing just now, you can reduce numbers of part of the product. You can reduce the material through the component integration as well. So this is more applicable to the integrated design just now. Integrated design, when you do from a modular, they have 2 or 3 chunks you can combine. That is an integrated design. You can reduce the component, you can reduce the cost of material, and then you can have more stylish design, but yet you need to think about how to manufacture it. For this reason, the DFM, the manufacturability is very important. They should begin during the design level or design stage as well. Like I said just now, when you learn manufacturing engineering, I already explained how concurrent engineering can contribute more on the design stage at design level for the manufacturable product. So that's why this is very important part at the level of design phase. So I hope you take note this one, and then we can have a more discussion in this topic. And then product development management. That is another one affecting your architecture modularity. Product development management. So if the functional element is implemented by 2 or more chunks as some integral architecture, so detailed design will require close coordination among different groups. So detailed design, they need coordination, need meeting, need coordinate between another group to another group, because that group maybe do the another things, this group do another thing. They have need coordination. So another possibility is to have several function elements allocate to the same chunk. So in this case, the workers or the group assigned to that chunk involved in the grid deal in the internal coordination across the large group. So when we combine, we integrate in the one group to do integrated design, so they involve with the similar group. So we can discuss inside group assigned. So we can have more internal coordination during design process. So we call it is product management. Product management, coordination, group to the group, internal coordination. So that is very important. And then modular and integral architecture has a demand from different project management style. So like a modular approach, like I said just now, they require very careful planning. During the system level design, they need to very careful planning, need to have a detailed person to see, to plan. But the detailed design is largely concerned. They need to do a detailing on design specification to ensure the product, the team assigned to that chunk meet the performance or product requirements, meet the cost, meet the schedule requirement when they design. So that is very important for the modular product management. But for the integral architecture, they have different style of the product development management. So for the integrals, they require the less planning. The modular, they need more planning, careful person to evaluate each chunk. But for the integrals architecture, they need more less on the planning. And specification during system level design, but they need the required more on the integration part, because they can combine all these elements, the function. They need more person to do integration, conflict resolution, coordination during detailed design phase. That is very important in the integral. The detail will require close coordination among different groups. So that is for the integrals. So not as easy for integral architecture doing, but there is the different style of development management for modular and integrated architecture style. And then design architecture design process. So we have to this step for design process to create schematic of product design, schematic clustering the element of schematic, create rough geometry layout, identify the fundamental and incidental interactions. So because the product architecture will have implication for product development activities. They have an implication of product development activities. So the result of this activity, is approximately geometry layout of the product, description of major chunk, and then documentation of the key interaction among the chunk. So that's why we need to consider all these 4 important process during the architecture design. So we go one by one for explanation how this can be met or conduct. Sorry. Okay. For creating product schematic, so everyone know, I think, the schematic design, product schematic diagram. So I think you learn in my class in the automation system and control, automation control and system control in the 4th year. And 3rd year, you learn already how schematic design using PLC, pneumatic. So that is all schematic design. So the schematic should reflect the team best understanding of the state of the product. So that is, we need to have that understanding and describe that one in the design. But it does not have a contents every imaginable detail. So we not need to put in the schematic design all details one. You just put the such as like for the printer just now, the send of paper condition, the printing trace, the horse powers. So that is all the schematic detail to describe the product as well. So need to have that understanding and then to describe that state of the product in terms of design of schematic. So this and another detailed function of element. So they have a, we can refer at a step for the product. A step. The schematic refer to the step also to produce. So we can refer that drawing, schematic drawing we create as a step. And then a good rule of the this one, we can aim to reduce our what I call it the chunk just now. If we have more than 30 chunk at the beginning, so we need to aim to reduce around 30 or below than 30 chunk inside our schematic design for the purpose of establishing the product architecture. So we need to create the product schematic first, and then to represent this flow of energy, flow of material, flow of signal and data using the block and arrows. So that is a like flow chart, like I call it the process. So that is a schematic. So I will show you later on the detail of this one. So then we need to cluster the schematic design. So when we create the schematic design, you need to have a clustering the element. So they have a geometric integration. They need to assign element in the same chunk, allow a single individuals and group to control the physical relationship among the elements. So the element required precision location or close geometric integration can be effect the best design if they are part of the same chunk. For the printer just now, this would be suggest clustering and the element associated with the positioning, for example, cartridge in the x-axis or positioning the papers in the y-axis. So the function sharing then can, when the single physical component can be implement several function element of the product. These function elements are best for the clustering together. We need to see for this example. So this is the schematic design for the printer just now. I said we have several chunks here for enclosed printer, provide structure support, store output, store blank paper, and then pick paper, positioning paper, X, Y axis, X axis, print cartridge. That is described in the different chunk or block. Of course, in this block, they have individual design later on. But to start, we need to create this schematic design for each chunk. So all chunk, they have an arrow here. You can see the arrow related interaction each chunk. So the clustering, what I said just now, for now they have 1, 2, 3, 4, 5, 6, 7, 8. So they have around 15. So when we make clustering, we have reduced to 1, 2, 3, 4, 5, 6, 7, 8, or 9 only to cluster using the clustering. So for enclosure, they have chassis, they have combined this one for paper tray. Of course, they have a store output and input. They have a paper tray. They put this one under print mechanism cluster for all this one, for the pickup paper, for cartridge moving in the SSC, YSC, they put in the print mechanism. And then controls, and then they have a user interface to see, to display. And then they have power cord cluster, they have host cluster, and then they have logic board. This one for the control, they have logic board cluster. Of course, they have communication with host, connect to the host. So all driver, everything lah. So this is a clustering. And then the challenge for this one is to combine, to group the cluster. When you grouping, maybe you can regroup again. So because this one not fixed, when you make, and then you go for the concept selection, so you can see whether this one suitable or not. You can arrange later on again, like puzzle, like puzzle. You can rearrange the clustering, rearrange or reduce the chunk. This one not suitable, for example. You can eliminate this one, you can combine to this one. So all this one can do it, but you need to start with the creating this plot, and then you need to clustering based on important function of your project. For example, this one for printer. All right. And then you need to create after you make a schematic design, drawing, you cluster it, and then you need to create a geometry, a rough geometry layout. A rough geometry layout can be created in 2 or 3 dimensions using the drawing models, using the physical model, using foam or cardboard. Also, you can make it, you can fabricate, like you do. I'm not sure in your time, but in my time last year, we did a GDP project. The student create the model using the board for prototype. So we can see the actual one using the physical model using from the cardboard. So that is creating the rough geometry layout. When you see the part from the 3D or 2D design, you can see more on the physical models. So they can show the layout. For example, in the printer just now, you can see the printer model. You can see the store papers, the height, and the positioning of major chunk. You can see from the rough geometry layout. And then by creating geometry layout, force the team to consider whether the geometry interface
among the chunk are feasible or not, or working or not. But this one you can see the relationship among the chunk during the creating this geometric layout. So that is very important as well. And then you identify the fundamental interaction and incidental interaction. So these two interaction is very important as well, because the product you create need to function, need to meet a performance. So need to see the fundamental interaction and incidental interaction. So this fundamental interaction is the planning one. You plan the interaction inside your product. So for example, you have a paper tray just now. So you put the sheet paper and the tray in the printer, and then the roller we rolls, and then we feed the paper inside the printers, and then the printer detects the papers, and then they make a little bit rearrangement, realignment, and then they start to print. The print mechanism begin while the papers load to the printers. So there is the interaction. So the interaction, fundamental interaction is the plan interaction, the planning. We well plan on that interaction, that movement. So the interaction is planned, and then it would be well understood, well planned, even in the earliest schematic design. So you need to plan before then. So for the incidental interaction, there is not planning one. Accidentally happen. So this one you also need to predict for the printer as well. Maybe when you put papers, then load the paper inside the printer, they have some vibration, for example. So when the roller start roll the papers in to the printer, and then the cartridge with moving, you can see you can sound the noise. You can see the cartridge moving, you can sound the noise. So the noise actually come with the vibration actually. So the vibration is the incidentally interaction. So you need to predict that one. What happened when this happen? Vibration happens. So what could be the interface? We need to set the precise location of the paper. If not, your printing become not exactly what you want. They have slanting a little bit, so you need to print again. You need to adjust a little bit the paper, go inside the printer. So that is the incidental interaction. Instead of a vibration, they also have thermal, for example, heating. So that is all you need to see. For example, load paper tray, they have vibration in the printing mechanism. So there is interaction you need to see. And then when printing begin, they have a thermal distortion. So they give a input. This one need to communicate with the RF interface logic board to nowadays they have a machine learning technologies. So when something happen, the machine can react based on the condition that happen inside the environment, that condition. That is machine learning. So for example, in the printer, the expensive printer for office use, for example, when you put the paper self arrangement, the self alignment inside. So because the machine learning, so what if the paper load maybe different way, but they detect and then they do a self alignment based on the condition the paper of they detect inside. They use a lot of sensor. That is how they react like human using the machine learning technology. So there is a control in the logic board. So this is another issue actually. But for this explanation, they have a incidental interaction graph. You can see in the books as well. So chassis as well, they have thermal dissociation, and then they send to the logic box as well to do a. So these all interaction you need to see. You need to do the draft or to predict, yeah, for the fundamental. This one you plan already, but this one for incidental interaction maybe not happen, but will happen. If it happen, what you should do, you should react, you know, in terms of design process. Okay. And then we go for the differential postponement. So before that, I think I give you 50-minute breaks, okay? Before we continue this part for toilet break, 1 hour. Is it okay? Everyone want to continue, or we just have a 5-minute break? Anis, okay? Irfan, okay?
We can have breaks.
Well, you have break, eh? Okay, 5-minute break. Okay, let's go. I pause here first, and then we continue here. We go for break first.